Introduction. Direct current machines were the first rotating electrical machines that were introduced to drive locomotives way back in 1839. DC machines are of two types, the DC generators and the DC motors. Click tabs to know more. DC generators. DC generators are electromechanical energy conversion devices which convert mechanical energy that is given to them from a prime mover to electrical energy. For example, industrial processes involving electroplating and electrolysis use DC generators as sources of supply. DC motors are electromechanical energy conversion devices that convert electrical energy to mechanical energy. They can have a wide range of speed, torque characteristics. As the speed of DC motors can be controlled easily, these motors are widely used in industries. Examples of DC motors are trains, elevators, hoists, rolling mills, etc. Constructional features. Construction of DC machines. A DC machine consists of a stator and a rotor with a uniform air gap in between. The stator, in case of DC machines, invariably carries the field windings and the rotor carries the armature windings. Magnetic frame or yoke. Yoke is made of cast steel for large machines of high rating and with cast iron for small machines of low rating. It acts as a protecting cover for the entire machine. It gives the mechanical support to the field poles. It provides the return path for the magnetic flux. Field pole core. Both pole core and pole shoe are made of cast steel or silicon steel. For large machines, lamination is required, whereas for small machines, it is not required. Pole core function. It accommodates the field winding and acts as a magnetic pole when the winding is excited. Commutator. The commutator is made of hard-drawn copper to reduce the wear and tear. Number of commutator segments is equal to the number of coils. Armature core. Armature core is made of silicon steel and laminated to reduce the eddy current losses. It accommodates the armature windings. It offers a low reluctance path for the magnetic flux. Slots. Hence, inductance is directly proportional to the flux as L is equal to N phi by I, where N is the number of turns, I is the current measured in amperes, phi is the flux measured in Webers, and L is the inductance measured in henries. Open slots are preferred because leakage flux reduces, hence inductance reduces, thereby commutation will improve. Armature slots are skewed to reduce the vibration. Brushes. Brushes are made of carbon or copper for small machines, electrographite for large machines, carbon graphite for large current machines. Function. The main function of brushes is to collect the current from the armature conductor through the commutator segments in a generator or lead the current into the armature conductor through commutator segments in a motor. Carbon will have more resistance and hence it fastens the commutation process. Carbon has a high thermal stability and it is required for operating the machine at a higher speed and a high load condition, and it has a lubricating property. Parts of DC machine. The DC machine mainly consists of the following parts: magnetic frame or yoke, field pole core and pole shoe, armature core, armature winding, compensation winding, rotor, interpoles, commutator, brushes. Click on each tab to learn more. Magnetic frame or yoke. In small generators, yokes are made of cast iron, but for large machines usually cast steel or rolled steel is used. The outer frame or yoke serves a double purpose. It provides mechanical support for the poles and acts as a protecting cover for the whole machine. It carries the magnetic flux produced by the poles. Pole. The magnetic poles of DC machine are structures fitted onto the inner wall of the yoke with screws. The construction of magnetic poles basically comprises of two parts, namely pole core and pole shoe. The pole core and the pole shoe are stacked together under hydraulic pressure and then attached to the yoke. Pole core. Pole cores are made of cast steel bolted to the yoke and are usually not laminated. Pole core is a small cross-sectional area and its function is to just hold the pole shoe over the yoke. The core supports the field windings which produce the necessary magnetic field. The field windings are wound around the cores such that they set up alternate north and south poles. Pole shoe. Pole shoes are laminated and composed of electrical grade cast steel sheets of 1 mm thickness and insulated from one another. Pole shoe, having a relatively large cross-sectional area, spreads the flux produced over the air gap between the stator and rotor to reduce the loss due to reluctance. The pole shoes also carry slots for the field windings that produce the field flux. Commutator. The function of the commutator is to convert the AC voltage induced in the armature conductors to DC voltage in the external circuit in general operation, whereas in DC motors, commutator produce unidirectional torque. The ends of the armature coils are joined to the commutator consisting of a small number of wedge-shaped segments or bars of hard-drawn or drop-forged copper. Commutator segments are insulated from each other with the help of thin layers of mica strips and from their supporting rings using mica cones and gaskets. The commutator is pressed onto the shaft. The assembling of the commutator requires great care since a little unevenness on its surface can cause undue sparking between the commutator segments and brushes. Brushes. Brushes are employed to collect current from the commutator and deliver it to the load. The rotating armature and the external circuit are connected through brushes. These are rectangular and are made of carbon, carbon graphite, graphite, metal graphite or copper. The graphite in the brush serves to lubricate the commutator. Individual brushes are supported in metal brush holders as shown in the figure. Studs attached to the rocker ring support the holder. The connection between the brush and brush holder is made through a flexible lead of braided copper wire called a pigtail or a shunt. Interpoles. The interpoles and their windings are mounted on the yoke and are located in the interpolar region between the main poles. The interpole is generally smaller compared to the poles. The interpole winding is composed of a few turns of a thick wire since it is connected in series with the armature circuit so that the magnetomotive force is proportional to the armature current. Interpoles. The interpoles and their winding. Rotor. The rotor is a rotating part in a DC machine. The rotor consists of the armature core, armature winding, commutator, etc. Armature. Armature core is made of silicon steel and laminated to reduce the eddy current losses. Functions. It accommodates the field winding and acts as a magnetic pole when the winding is excited. It also accommodates the armature windings. It offers a low reluctance path for the magnetic flux. Armature core. The armature core is a rotating part of a DC machine. It houses the armature conductors or coils. In order to reduce eddy current losses, the laminations are insulated from each other. Slots are punched at the periphery of the core as shown in the figure. In small machines, the armature stampings are keyed directly to the shaft. Usually, these laminations are perforated for the air ducts which permit axial flow of air through the armature for cooling purposes. Armature winding. The rotor carries the armature winding in a DC machine. The armature winding coils are placed in the slots. The coils are insulated from one another and from the armature core. The armature winding coil ends are connected suitably to the commutator segments. The windings consist of straight conductors arranged parallel to the shaft, housed in slots and grouped round the periphery of the armature core. The induced EMF per conductor is small, that is a fraction of a volt for a small machine and only a few volts for large machines. So we require many conductors for production of rated voltage. Armature windings. The armature winding is a main current-carrying winding in which the electromotive force or counter EMF of rotation is induced. The armature windings of DC machines are located on the rotor since they must operate in union with the commutator. The current in the armature winding is known as the armature current. The location of the winding depends upon the type of machine. Armature winding. The rotor carries the armature. Compensation windings. Compensation windings are connected in the same way as the interpole windings, but they are located in the axial slots of the field pole shoe. Compensating windings are used for large DC machines to neutralize the cross-magnetizing effect of armature reaction. End belt structure and bearings. End belt structure is mechanically connected to the yoke. They contain the bearings that support the armature shaft. The end belts are structural covers that enclose the machine. In some machines, the end belts support brush rigging, which in turn support the brushes. Classification of armature windings. Depending upon how the ends of the armature coils are joined to the commutator, armature windings can be classified into two categories such as lap winding and wave winding. Click on tab to know more about lap and wave winding. Lap winding. In lap winding, the two ends of a coil, designated start and finish, are connected to adjacent commutator segments. The figure shows the connections of the coils to form a lap winding. Since the sides of the successive coils overlap each coil, the winding is known as lap winding. Wave winding. From the figure, it can be seen that the finish F of one coil and the start S of another coil are connected to the same commutator segment. In this manner, the coils are progressively connected and the winding goes around all the poles till it returns to the coil side from where it started. The figure shows the coils connected in wave winding. A wave winding has only two parts in parallel between the positive and negative brushes irrespective of the number of poles. Thus, for a wave-wound armature, the total current at the terminals of the DC machine is twice the current in one path of the winding. Comparison between lap and wave windings. The number of parallel paths in lap winding is equal to the number of poles P and the number of parallel paths is 2 in wave winding. Number of brushes in lap winding is equal to the number of poles P, whereas in wave winding the number of brushes are minimum 2, but actually P brushes are used. The current in each coil is IA divided by A, where IA is the armature current and the current in each coil in wave winding is IA divided by 2, where IA is the armature current. Principle of operation of DC machines. A single-turn rectangular copper coil rotating about its own axis in a magnetic field provided by either permanent magnets or electromagnets is shown on the screen. The two ends of the coil are joined to two commutator segments A and B, which are insulated from each other and from the mechanical shaft. Two collecting brushes of carbon or copper press against the commutator segments. Their function is to collect the current induced in the coil and to convey it to the external load resistance R. The rotating coil may be called armature and the magnets as field magnets. Working of simple generator AC. When the plane of the coil is at right angles to the lines of the flux, that is when it is in position 1, the flux linked with the coil is maximum, but the rate of change of flux linkages is minimum. Hence, there is no induced EMF in the coil. As the coil continues to rotate further, the rate of change of the flux linkages and hence induced EMF in it increases till position 3 is reached, where theta is equal to 90 degrees. The coil plane is horizontal, that is parallel to the lines of the flux. The flux linked with the coil is minimum, but the rate of change of flux linkages is maximum. Hence, maximum EMF is induced in that position. From 90 degrees to 180 degrees, the flux linked with the coil gradually increases, but the rate of change of flux linkages decreases. Hence, the induced EMF decreases gradually in position 5 of the coil, where it is reduced to zero value. From 180 degrees to 360 degrees, the variations in the magnitude of EMF are similar to those in the first half of the revolution. Its value is maximum when the coil is in position 7 and minimum at position 1. But it is found that the direction of the induced current is the reverse of the previous direction of flow. Working of DC generator. A single loop generator with each terminal is connected to a segment of a two-segment metal ring as shown on the screen. The two segments of the split metal ring are insulated from each other. This forms a simple commutator. For the remainder of this discussion, refer to the graph shown on the screen, that is part A through D. This gives a clear description of the operation of a DC generator. When the armature loop rotates in a clockwise direction, from position A to position B, a voltage is induced in the armature loop which causes a current in a direction that deflects a meter to the right. Current flows through the loop out of the negative brush, through the meter and the load and again moves back through the positive brush to the loop. voltage reaches its maximum value at point B. The generated voltage and the current fall to zero at position C. At this instant, each brush will get in contact with both the segments of the commutator. As the armature loop rotates to position D, a voltage is again induced in the loop. In this case, however, the voltage is of opposite polarity. The voltages induced in the two sides of the coil at position D are in the reverse direction to that of the voltages shown at position B. Note that the current is flowing from the black side to the white side in position B and from the white side to the black side in position D. However, because the segments of the commutator have rotated with the loop and are contacted by opposite brushes, the direction of current flow through the brushes and the meter remains the same at position B. The voltage developed across the brushes is pulsating and unidirectional in one direction only. It varies twice during each revolution between 0 and maximum. This variation is called ripple. A pulsating voltage, such as that produced in the preceding description, is not suitable for most applications. EMF equation. Let phi be the flux by pole measured in Webers, Z be the total number of armature conductors, P be the number of poles, A be the number of parallel paths, that is 2 for wave winding and P for lap winding, N be the speed of armature measured in rate per minute, EG be the EMF of the generator or EMF per parallel path measured in volts. Flux cut by one conductor in one revolution of the armatured D phi is equal to P phi measured in Webers. Time taken to complete one revolution dt is equal to 60 divided by N measured in seconds. The EMF generated per conductor is equal to d phi divided by dt, which is equal to P phi divided by 60 by N, which is equal to P phi N divided by 60 measured in volts. EMF generated EG is the EMF per parallel path, which is equal to EMF per conductor multiplied by the number of conductors in series or parallel path. This is equal to P phi N divided by 60 multiplied by Z divided by A. Therefore, EMF generated EG is equal to P phi Zn divided by 60A measured in volts, where A is equal to 2 for wave winding and equal to P for lap winding. Derivation for generated EMF EG. EG depends on the following factors: the magnetic flux phi Webers, the speed of the machine is revolution per second or revolution per minute, a constant that depends on the construction of the machine, the EMF EG in a conductor of the active length L moving at a velocity in a magnetic field having flux density B is given by EG is the product of BLV. Let phi be flux per pole Webers. P is the number of generator poles. Z is total number of armature conductors. A is number of parallel paths. B is magnetic flux density, Tesla. The number of conductors in series is given by Z divided by A, where Z is number of conductors and A is number of parallel paths. The EMF generated is given by the flux density B can be expressed as B is equal to the product of flux per pole and number of poles divided by cylindrical area of armature surface. B is equal to product of phi P divided by 2 pi RL, where R is radius of armature and L is the length. Velocity v is equal to product of 2 pi rn divided by 60. By substituting these values in Eg, we get the following equation. Eg is product of phi zn p divided by product of 60 a.